Let's look at a third example of using Ampere's law to work out a magnetic field. This is a toroid, which is a ring, a torus, which has wires wrapped all around it in a spiral pattern. So it's actually very much like a solenoid, only all wrapped in a circle. So what's the magnetic field doing here? Well, as usual, step 1, draw. If we had a solenoid, the magnetic field is strong down the middle and very weak outside. So if we take our solenoid and bend it into a circle, presumably we're going to get a strong circular field inside and not much outside. Okay, so we're assuming there's some strong circular field. Which way is it going? So let's take the right-hand rule over here. That wire's going left, so by the right-hand rule, the magnetic field inside must be going around this way. Try over here, right-hand rule. It's the same. Okay, so we've got a magnetic field going along like that. The question will then be, how strong is it going to be? So then we get to step 2, pick your loop. As normal, you want a loop which is going to be easy to calculate and simple. In this case, the simplest possible loop is just go around inside the circle. So maybe in the middle here, going all the way around. So if you look down it from on top, you get the toroid and you get a loop around the middle somewhere. Why is that a good one? Well, because if it's nice and simple in the middle, it'll be pointing the same direction as the magnetic field everywhere. So then we get to step 3, use Ampere's law. So the line integral around this loop is just the usual magnetic field times the line element. That's equal to mu naught times the sum of the currents. Now the sum of the currents, let's say there are n loops of wire and a current I, that's just equal to mu naught times n times I, because we're only looking at the ones inside our loop. Just imagine drawing our imaginary soap film over the inside. The wires on the inside are in and the ones on the outside are not. Meanwhile, what's B dot dl? They're in the same direction, so the cos theta goes away, so it's just going to be equal to the mod of the magnetic field times the length of the circle. If the circle is in the middle of the toroid, so the radius here is the radius from the center to the middle of the toroid, that gives us just 2 pi r. So what we find is that the strength of the magnetic field is just equal to mu naught times the number of loops times the current in the loop divided by 2 pi r. And that would have been an extraordinarily difficult calculation to do any other way, let's say using the Biot-Savart law, whereas here it's pretty easy. And it tells us right away that the magnetic field must be stronger on the inside where r is smaller than on the outside, which I wouldn't have guessed otherwise.